Okay, in this video 1.2, we're going to talk about solving word problems using systems of equations. I'm going to go through 4 different word problems, one that I consider stupid, a less stupid word problem, mixing fluids, and a distance equals rate times time problem, and then talk about the general setup for word problems overall. Again, you can jump down to the bottom and look at the info and skip to parts that you need or want to see. On the left side here, I have the steps I follow for solving a word problem. Read and understand the problem, which a lot of people skip, and it's terribly, terribly important to actually do this. By which I mean, don't just try and start writing down numbers right away, but understand what the problem is asking you. So here's the stupid word problem. I'm going to do step 1 now, read and understand it. You look into a barn full of cows and ducks, and you see 17 heads and 56 feet. How many cows and how many ducks are in the barn? Well, first of all, this is a stupid problem for so many reasons. Like, why are cows and ducks in a barn in the first place? And why are you counting heads? Like, if you see a head, you would know it was a cow's head and just say a cow. Or how can you count 56 feet? Like, aren't they walking around and moving? And when you see a foot, wouldn't you say, hey, that's a duck's foot, not a cow's foot? It's a very, very silly problem. And a problem I don't want to do more than once, because I think doing a stupid problem can be easy, it can be simple, and it can help us learn how to set these up. So that's the value of doing a stupid word problem like this. There are problems like this that appear on state tests and national tests because they can be done a bunch of different ways, but I'm going to show one specific way. So basically we're looking into the barn and trying to figure how many of each animal is in there. We know that each duck and each cow has only one head, but we know that a duck has 2 feet whereas a cow has 4 feet. And those are going to be the 2 differences that we use. So there, I've done step 1. Step 2 is no, seriously do step 1, because if you don't do step 1, you're in trouble. Step 3 is you take what you're trying to find, and define that as your variables. I'm trying to find X is going to be the number of cows in the barn. Don't just write cows. It has to be something that can be expressed numerically. Like if I just wrote cows, that can be number of cows, weight of cows, age of cows. It can mean all those different things, so be specific. I want to find the number of ducks. And I could have used C and D for my variables. You can do it if you want to, but I'm going to stick with X and Y. So there, I've done step 3, set up variables, define variables. Always, always do that as the first step you take to write things down. Use information from the problem to set up equations. Well, here's what I know. 1 head per cow plus 1 head per duck has to equal 17 total heads. This was my heads equation. It's head plus head equals heads. The second equation, sorry I lost this, the second equation is going to be about feet. There's 4 feet per cow and 2 feet per duck, and altogether there's going to be 56 feet. The units have to match. The units are incredibly important here. Feet plus feet equals feet. So for example, if there were, say, 3 cows, that would represent 12 feet. And if there were, say, 10 ducks, that would represent 20 feet. And altogether, 12 plus 20 would be 32 feet. Now, we don't need 32 feet, we need 56 feet. And we need more than 13 animals total. But the idea here is the units have to match. Think about this. What is 8 heads plus 20 feet? And that even it looks like I wrote the word hands instead of heads. It doesn't matter. It makes no difference. You can't add up different units. 8 heads plus 20 feet isn't 28 heads or 28 feet. And it's not 28 head feet. That doesn't mean anything. You can't do it. That's part of why you can't add unlike terms, because it doesn't actually make any sense. The units have to be matching in such a way that you can actually combine them. But now I have set up my equations. I can solve. I can solve this by substitution, elimination, or graphing. It doesn't matter which method you use. Pick whichever looks best. These always eliminate really well, but this one also substitutes really nice. I think I'm going to eliminate this one just because I can. So I'm going to multiply the top equation by -2. That's going to cancel out the y's. So I'll have -2x minus 2y equals -34. I add these up and I get 2x equals 22. So x equals 11. If you don't remember how to solve by substitution or elimination, you can watch my last video, which I'll link below and might appear on the screen right now magically. Now if x equals 11, I'm going to plug that back in up here. If x equals 11, y must be 6. There are going to be 11 cows and 6 ducks. Let's check to make sure that gets us the right number of feet. If I plug in 11 here, 11 times 4 is 44. I plug in a 6 here, 2 times 6 is 12. 44 plus 12 is 56, so it checks. Oh my goodness, you have to check. You just have to do it. Because you want to get it right, and you want to know you got it right. And checking doesn't take that long, and it can save you a whole world of hurt in the future. And I know you don't want to check because you don't want to be wrong. If you're wrong, you have to go back and do more work. And if you don't know if you're wrong, then you don't have to go back and do more work. But get over it. Check it. I'll stop yelling at you now, sorry. Here's a less stupid word problem. You work at your school store selling sweatshirts and mugs and jackets and things. One day you sell jackets for $40 each and t-shirts for $12 each, and at the end of the day you lost all your receipts. You know you sold a total of 10 articles of clothing, jackets or t-shirts, and collected $288. How many jackets and how many t-shirts did you sell? This is a less stupid word problem because this can actually happen, and this can come up, and processes like this you might actually have to follow at some point. Part of why I think it's kind of silly is because it's so contrived. It's going to work out to a really nice, pretty answer, and that won't always happen. I guess in this type of situation it would. But we're going to go for it. First thing to do is define variables. Pause this and ask yourself, what should the variables be? Have you paused it? Good. I'm going to go. X is going to be number of jackets. Not just jackets, but number of jackets, and that's important. If you want to be really precise, you can say number of jackets sold. And Y will be number of shirts sold. Again, pause it. See if you can make equations. We're going to make 2 equations, see if you can find them. If we sold 10 articles of clothing, X plus Y equals 10. If altogether we made $288, well, we know we're doing $40 per jacket, and we're doing $12 per shirt, and those 2 things combined have to be $12.88. See, this was clothing, 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 it matches. This was money, 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 it matches, because 40x represents the total money that comes from jackets, okay? 40x is the total amount of money coming from jackets. So if you sold 5 jackets, well, X stands for 5, you sold 5 jackets, number of jackets sold was 5, you made $200 off jackets. So we're going to solve this. Again, we can use substitution or elimination. It doesn't matter. Since I used substitution, nope, I used elimination last time, so I'll use substitution this time. So I'm just going to clean up my board real quick. Believe it or not, even though I write real fast and messy, I like things to be pretty for me. I like to have the space. I am going to get this x by itself. I subtracted a y from both sides. I will then take this and plug it into the other x. So that becomes 40 times 10 minus y plus 12y equals 288. So 400 minus 40y plus 12y equals 288. I distributed this. So I combine these 2 terms and I get negative 28y, and I subtract 400 from both sides. I get negative 112. And I really hope this comes out to 4. I'm going to divide both sides by 28, really by negative 28, but the negatives cancel. And that is 4, thank goodness. So y equals 4. If we sold 4 shirts, then we sold 6 jackets. Now, since I've already defined x to be number of jackets sold, if I just say x equals 6, I know I sold 6 jackets because I defined my variables so well. And I know that I sold 4 shirts. Okay, I'm going to talk about something very different now. This is not a stupid problem, but actually, I shouldn't call lesson stupid. Anyways, this is a problem that happens, and a problem that's worth doing. We are actually going to work our way to this problem. That's the problem we're going to try and build our way up towards. But I think oftentimes students don't understand percentages and ratios as opposed to amounts. So here's what I mean. Suppose that you took a bottle of lemonade that was 20% sugar. And then you mixed it with one bottle, the same size bottle of lemonade, that is 50% sugar. The new mixture will be what percent of sugar? Please pause the video and think about that question, or at least think about it as I talk about it. If you're mixing 2 bottles of lemonade that are 20% sugar and 50% sugar, the new mixture will not be 70% sugar. And that's what people often do, is they want to add up the percentages. But these aren't amounts, they're ratios. 20% means out of every 100 bits, 20 bits are going to be sugar. Like out of 100 drops maybe, but drops is, you can't think of sugar that way. So it's a ratio. So I'm taking what's weak, I'm going to call this the weak lemonade, and I'm going to call this the strong lemonade, meaning it's going to be really, really sweet. And as they combine, the weak makes the strong weaker. It dilutes it. And the strong makes the weak stronger. It's adding more sugar to it. The ratio is going to be somewhere between 20 and 50. In fact, because we're adding the exact same amount, because they were both one bottle of sugar, it's going to be 35% sugar. So let me see if I can illustrate that better. Here, gosh, it's an awful, awful bottle. So I'm just going to pretend like it's a beaker. You know, I'm going to talk about science. Here's a beaker. And this was 20% sugar, meaning it was also 80% other stuff. Maybe water, who knows. We'll say 80% other stuff. Well, the next bottle was going to be 50% sugar, meaning it was also 50% of the other stuff. Well, these two things are going to average each other out. This is going to go up while this goes down. The sugar in the weak one goes up, the sugar percent in the strong one goes down. Had it just been grams, though, suppose we had instead of 20%, 20 grams of sugar, and one is 50 grams of sugar. Well, that is an amount, not a percentage. So when we put them together, yes, that would actually make 70 grams of sugar, but the percentages would still be different, because a percentage is a ratio, not an actual amount. So suppose now, instead of us doing two bottles of the same size, one of them was small and one of them was 4 times bigger. We're doing 5 milliliters of 20% sugar with 20 milliliters of 50% sugar. If we were to combine these, what would the new ratio be? Pause it and try and answer this. And if nothing else, pause it and think about, is it going to be closer to 50 or closer to 20? And maybe how much closer? Well, now we have a small bottle and a bottle 4 times bigger. So obviously, this one is going to have a much, much larger impact on the final results. So one way to do this problem is to figure out how much actual sugar is in each bottle. Like if we have a 5 milliliter thing of lemonade and 20% of it is sugar, well then how much actual sugar is in there? What I can do is calculate 20% or 0.2 times 5, and that's actually 1. That means that there's 1 milliliter of dissolved sugar inside the first bottle. It has 1 milliliter of sugar. The second one is 20 milliliters in size, so it's much, much bigger. And it has 50% sugar. So instead of multiplying it by 0.2, I do 0.5, and that gets me 10. There's 10 milliliters of dissolved sugar in the second bottle. So when I combine the two together, if I add the two up, I'm going to have 11 milliliters of dissolved sugar out of a total possibility of 25 milliliters of juice. Of lemonade. Because the 5 milliliters plus the 20 milliliters gives me 25 milliliters. So there's the amount of sugar out of the total juice. So now we'll divide them and find the percentage. One more clear. 11 divided by 25 is going to be 44%. 0.44, 44%. So the 20% sugar drink, because it was so much less in its amount, meaning the 5 milliliters was so small compared to the 20 milliliters, it had a much smaller impact on the overall size. It just brought it down 6%. It dropped from 50% to 44%. So I hope you're recognizing the difference between the size of sugar and the percentage of sugar. I'll say it different. The amount of sugar versus the percent of sugar. Amount is like an amount, whereas a percentage is a ratio, a comparison of two things. So now we're going to do this problem here. This is the problem that is very commonly done in these scenarios. You have lemonade of two different strengths. One is 20% sugar and one is 50% sugar. How much of the two lemonades should you mix to result in 50 liters of lemonade that is 30% sugar? So we're making a ton of lemonade here. Maybe we're going to try and sell it all. Maybe we're going to try and give it to all the football teams at a football camp. That's a ton of lemonade. I shouldn't say ton, because it's probably not literally a ton. It's a lot of lemonade. And we wanted to come out just right to 30% sugar. Well, pause the video and think to yourself, am I going to need more of the weak stuff or more of the strong stuff? And ask that question, answer that question first. Which will you need more of, weak stuff or strong stuff? You are going to need more of the weak stuff because halfway between 20 and 50 is 35. And since we're going closer to 20 than 50, we're not going to go quite halfway. We want more of the weak stuff. Had 30 been closer to 50 than 20, we would have wanted more of the strong stuff. So when we're done, our answer should have more weak stuff, 20%, than it should strong stuff. So I hope you understand we're taking two types of lemonade, mixing them to try and get the desired amount, a good tasting lemonade, which in this world is 30% sugar. Well, what are we trying to find? I'm going to have X stand for liters of 20% sugar drink. And Y will stand for liters of 50% sugar drink. Those are the two things I'm trying to find, X and Y. And we're going to assume that we just have enough of these two to not worry about, like, we have basically an unlimited supply of 20% sugar and 50% sugar drinks. Well, I have two things that I know. Altogether, the two drinks are going to give me 50 liters. So X plus Y equals 50. This was my liters, my total amount of lemonade mixtures. X plus Y equals 50 because it's X stands for liters, Y stands for liters, so liters plus liters equals liters. Next, I have to do the amount of sugar. I only want the process that I'm done with to be 30% sugar. So when I'm all said and done, I want 30% of this lemonade to be sugar, which I have no idea if that's high or not. My guess is that's pretty high. I know that I've got 20% sugar and 50% sugar combining to get me to that 30%. So I'm going to write this prettier now. I have X plus Y equals 50, and I have 0.2X plus 0.5Y equals 30% times 50, I think it's just going to be 15. 10% would be 5, would be 3 5, so it's 15. This is the system of equations I want to solve. You can solve this by substitution, elimination, or graphing on your calculator or Desmos or whatever, it doesn't matter. Remember that if you don't like the decimals, you can multiply all of this by 10. I kind of wrote that weird, but multiply everything by 10, and the bottom becomes 2x plus 5y equals 150. That just kills the decimals if you want to. I'm going to solve this by elimination. I'm going to multiply the top and the bottom by, just the top equation by -2. That gets me -2x minus 2y equals -100, and 2x plus 5y equals 150. I add these up and I get 3y equals 50. So y equals 50 over 3, which is 16 2/3. Prove that to you. 16.6. Since we're just doing liters, I don't need to worry about the whole decimal being perfectly precise. Y is going to be 16.7 liters. If y is 16.7, I can plug that in for this y. I'm going to get that x is 33.3. These are the amounts of the two different types of lemonades I should be mixing to get the desired results, which is 50 total liters coming out at 30% sugar. And if I wanted to check this, I would take these numbers, x and y, and plug them into both equations to make sure that they work. Now that check only works if your equations were actually correct in the first place, but we got to start somewhere. It is a good sign that we needed more of the weak stuff, because remember, x was the weak stuff, and we needed more of the weak stuff, which we said in the beginning was going to be the case. Now this type of problem we did with sugar, but it's also often done with acids or with medicines. It's a chemistry problem that can come in pharmacy, nursing, all sorts of medical applications, and science applications. Next, I'm going to talk about riding your bike, distances and times. I live in Eugene, Oregon, in the Pacific Northwest. And we do a funny thing here that you might also do where you're from, but you might not. If I ask somebody, how far is it from Eugene to Portland? I do this in class every year. How far is it from Eugene to Portland, Oregon? They'll say, about 2 hours. In the Northwest, we tend to give distances as times. I asked how far it was, and the distance is actually about 120 miles. That is the actual distance. But we tend to list things as times because it takes about 2 hours to get there. Because in our neck of the woods, there's not a ton of traffic. So you can kind of say time instead of distance. But that is not what a distance is. A distance is an actual length. It is not a time. To find distances, we use the equation distance equals rate, meaning your speed, times time. Distance equals rate times time. We often call it dirt. D equals RT. If you can ride your bike at 22 miles per hour, and you've already traveled 15 miles, how far will you ride if you continue to ride for another hour and 20 minutes? So you've already rode 15 miles, you're going to keep riding for an hour and 20 minutes. We want to find your distance. Well, your total distance is going to be, you're traveling at 22 miles per hour, you're going to ride your bike for another hour and 20 minutes. And an hour and 20 minutes, you have to think about minutes as being out of 60. That's 1 1/3 hours. 1 1/3 or 4/3, I'm going to call it. 1 1/3 hours. You have to take that 20 minutes and make it out of 60, because 20 minutes is a third of an hour, so it's 1 1/3 hours. Plus, we've already gone the original 15 miles. Here was the starting amount. Here is our rate, and here is our time. This is essentially a y equals mx plus b equation. This is your starting amount. This is going to be rate and time, dirt. So I do 22 times 4/3 plus 15. .3 miles. The total distance was 44.3 repeating miles. Notice how in these problems we're not working with super pretty numbers. They're now going to come out real clean and whole, and that's how it's often going to be with these sorts of things. So we had to travel 15 miles plus the additional distances from the rates and times. Now please understand, this is a distance. I don't know what it is at this point. I knew what it was once I did the calculations, but this represents a distance, and this represents a distance. So we have a distance equals a distance plus a distance. When you have a rate times a time, that is the same as a distance. That's why we say distance is rate times time. This is a distance, this is a distance. They're equal to each other. Two trains are heading towards each other. This is the classic algebra problem that you always see in movies and TV shows and people stress out about. And they wonder, what's the point of it? Why would I ever learn this problem? Because it's actually quite valuable when you're trying to beat somebody somewhere or meet somebody somewhere. And I think it's got a lot of value to it. Not a stupid problem. Two trains are heading towards each other. One train leaves New York heading west at 220 miles per hour. The other train leaves San Francisco heading east at 200 miles per hour. If New York and San Francisco are 3,000 miles apart, at how many hours will the two trains meet, and how far will they have traveled? Lots of things here for us to consider. I think it's really helpful to start by just drawing out a number line, actually. Here's a big number line. And way over here on this side will be San Francisco, and way over here on this side will be New York. And they are 3,000 miles apart. Well, we've got these two trains heading towards each other. I'm just going to make up two names, just kind of randomly off the top of my head. Let's call this train Thomas, And that was a dark blue. I should probably change the color of that blue. This train will be Thomas. Yeah, that's the one. This train will be Thomas. And the train over here we'll just call Percy. I'm just making up names. Ooh, that's a bad train. But you're not here to see me draw trains. You're here to see me solve some math. These trains are heading towards each other. I can make an equation for each. Thomas, his distance equals rate times time equation, he is traveling 200 miles per hour. So his distance equals rate times time is what I'm doing. His rate is 200, his time we don't know, and his distance we don't know, but his distance is determined by the rate and the time. So for example, if he's been going for 5 hours, that'll be 1,000 miles. And if he's gone for 15 hours, that'll be 3,000 miles. So if Percy wasn't going at all, if Percy wasn't moving, this would take 15 hours. But Percy is moving. So instead of Thomas having to go the whole entire way, Thomas is going to go for a while, and Percy is going to go for a while, and they're going to meet somewhere in the middle. Pause and ask yourself this question. Do they meet closer to San Francisco or closer to New York? And right now we're making some assumptions like they're going the same speed the whole time. If you know anything about when the railroad was built, the people that built in the westward direction from the Atlantic towards the Pacific covered way more ground than the people who built in the eastward direction from the Pacific towards the Atlantic, because the people starting on the right side of the map, the east side, got to go on flat territory. They covered all these plains. They can go really fast. The people on the other side had to go over mountains. Anyways, history's over. Let's talk about Percy. Percy, his distance, we're going to have him going in the opposite direction. He's traveling backwards 280 feet per second, or sorry, 220 miles per hour. And he has to travel starting at the point 3,000. I'm going to call this the point 3,000, and this the point 0. Thomas is starting at 0, Percy is starting at 3,000. Since Percy is going backwards, meaning in the opposite direction, he has a negative slope. That negative slope just means it's the other direction, the opposite direction. Now the question is, at what point, or how much time are these two trains at the same point? Meaning, when are their distances the same? And by that I mean the same distance from 0. Because if they're both the same distance from 0, which we're calling San Francisco, then they'll be at the same point. So if they have the same distance, that means these two distances are the same. I can take one of these and plug it in for the other. I'm going to solve this equation. Negative 220t plus 3,000 equals 200t. Get the t's together on the same side. And you get 3,000 equals 420t. Divide both sides by 420. And t is going to equal whatever 3,000 divided by 420 is. .14 hours. Because of the time. It takes them a little over 7 hours. In fact, if you want to make that minutes, 7 hours, 8 minutes. A little over 7 hours. Now, that was at how many hours will the two trains meet? We just answered this part. We've also got to answer this part. How far will they have gone? So I'll take this 7.14 and plug it in for this t and plug it in for this t. Because Thomas is not going to travel as far as Percy because Percy is going faster. They're going to meet closer to Thomas than they are to Percy, closer to San Francisco than New York. So I'll do 200 times my previous answer. Nope, never mind. 200 times 7.14, which is 1428. And I'll do 220 times 7.14, 1570.8. That's how far Thomas and Percy travel. These are both in miles. Now, quite frankly, there's an easier way to set this up. There's also an easier way to set up the, well, maybe not, okay, I'll do one thing at a time. There's an easier way to set up this problem, but I want you to understand it before I show the easier way. Here's the understanding. Thomas is going one direction, positive. Percy is going the other direction, negative. And Percy's starting way, way, way further. But you can think of it this way. Together, the two trains together are going 420 miles per hour. The two trains together are covering 420 miles because every hour he goes this far and he goes a little bit further. Every hour they're chewing up that much distance. If they're going 420 miles per hour and they have to chew up a total of 3,000 miles, the question is how long will it take to do 3,000 divided by 420? And that's exactly what we got with this process. We got 420, which was this plus this. That got us 420. Then we did 3,000 divided by 420. It's a very healthy way to think about this. They're covering 420 miles per hour. They've got to go 3,000 miles, so it's going to take a little over 7 hours. All of these problems set up in one of two ways for the most part. Not all, but most of them. I call it either side by side, where you have a standard form equation with the x's and the y's together. And if ever you mix things or combine things, you have cows and ducks or shirts and jackets or lemonades, things that are being mixed up together, it's often going to set up in this form. Usually, you have x plus y equals something, and then a coefficient on x, a coefficient on y, and a coefficient on the something. Not always, but usually. If you have an independent or dependent variable, then there's usually two scenarios, like a Thomas scenario and a Percy scenario. Or like if we do Verizon and AT&T and compare their coverages, there'll be a Verizon scenario and an AT&T scenario. Whenever there's an independent variable, or like a slope or a rate or something that's changing all the time, you're going to use this setup, independent dependent, which is actually slope-intercept form, y equals mx plus b, over and over and over. I recommend you study these two slides and read them over. Very, very useful stuff here. Another long video, but I hope it was worth your time. Thanks for watching. Have a nice day.